Time doesn't care that you're reading this right now. It moved forward while you blinked. It'll keep moving long after you've forgotten this sentence. But here's what nobody can quite explain. What exactly is moving? We measure time obsessively. Seconds tick by on screens. Watches vibrate on wrists. Calendars fill with obligations stretching into months we haven't lived yet. Every civilization that's ever existed has tracked time's passage. Yet if you ask a physicist what time actually is, the answer gets uncomfortable fast. We've built our entire world around something we can't define. Stand perfectly still. You're hurtling through space right now at hundreds of miles per second. Earth spins. Earth orbits. The solar system spirals through the galaxy, but you feel none of it. What you do feel is time passing. That sensation seems absolute, doesn't it? 1 second for you equals 1 second for everyone else, except it doesn't. Einstein proved that a century ago, and we still haven't wrapped our heads around what that means. Let's start with what seems simple. Ancient humans watched the sun rise and set. They noticed the moon's phases, seasons cycled, patterns emerged from chaos. The first calendars weren't just tools, they were revelations. Time could be predicted. The future, at least partially, could be known. Stonehenge might be a temple, but it's also a clock. So are the pyramids. Our ancestors were desperate to understand time's rhythm because rhythm implies structure, and structure implies meaning. But rhythm isn't the same as understanding. A pendulum swings at regular intervals. Does the pendulum understand time? Your heartbeat marks duration. Does your heart know what duration is? We've confused measurement with comprehension. The Egyptians divided day and night into 12 parts each, giving us our 24-hour day. Completely arbitrary. The Babylonians gave us 60-second minutes and 60-minute hours, based on their number system, not on anything fundamental to time itself. We've been making it up as we go. Here's where it gets strange. Imagine you're holding a clock while standing on Earth. Now imagine your twin takes an identical clock onto a spacecraft and accelerates to near light speed. When your twin returns, less time will have passed for them. Their clock will show it. Their body will show it. They'll be younger than you. Not by much if the trip was short, but measurably, undeniably younger. Same clocks, same mechanisms, different amounts of time experienced. This isn't theory. We've tested it with atomic clocks on airplanes. Time genuinely passes at different rates depending on how fast you're moving. What does that mean? If time can stretch and compress based on velocity, what is it stretching and compressing within? Space and time aren't separate. They're woven together into what Einstein called spacetime, a four-dimensional fabric that bends, warps, and flexes. Massive objects create dips in this fabric. We call those dips gravity. A black hole creates such an extreme dip that at its edge, time nearly stops relative to an outside observer. Fall toward a black hole's event horizon, and from your perspective, everything happens normally. But someone watching you from a safe distance would see you slow down, freeze, never quite cross that boundary. You'd experience time. They'd watch you become a statue. Does time exist without change? Picture a universe frozen solid, every particle locked in place. Nothing moves, nothing decays, nothing transforms. Would time still pass in that universe? You might say no, nothing's changing, so time isn't flowing. But then, what is time? Just change itself? Or is it the stage on which change performs? Philosophy and physics collide here, and neither has a knockout punch ready. Consider entropy. The second law of thermodynamics states that in a closed system, disorder always increases. Drop a glass, it shatters. You'll never see shards spontaneously leap off the floor and reassemble themselves. Heat flows from hot to cold, never the reverse. Entropy gives time a direction, an arrow pointing from past to future. This is why we remember yesterday, but not tomorrow. Memory requires order, structure. The past is relatively ordered compared to the future's chaos. Your brain can encode memories of what already happened, because those events left structured traces. The future hasn't happened yet, hasn't left traces, remains a blur of probability. But the laws of physics at the fundamental level don't care about direction. Newton's laws work the same backward or forward. Maxwell's equations describing electromagnetism are time-symmetric. Even Einstein's relativity doesn't prefer one direction over another. Quantum mechanics gets weird about it, but mostly physics says time could run either way. Yet it doesn't. Eggs scramble, never unscramble. We age forward, never backward. Why? Nobody knows. That's not an exaggeration. We genuinely don't know why time has an arrow. Entropy explains what the arrow does, but not why it exists. Some physicists think it's connected to the Big Bang. The universe started in an extremely low entropy state, incredibly ordered, and has been sliding toward disorder ever since. But why did it start that way? Why was there a beginning at all? 13.8 billion years ago, everything we can observe was compressed into something smaller than an atom. Then it wasn't. The Big Bang wasn't an explosion in space. It was space itself expanding, carrying matter and energy along for the ride. Time began then too. Not that time was waiting around for the starting gun. Before the Big Bang, before might not mean anything. Time could be a property of our universe, something that only exists within it. Ask what came before, and you might be asking what's north of the North Pole. The question contains a category error, unless it doesn't. Some models suggest our universe could be one bubble in an eternal froth of bubble universes, each with its own timeline. Others propose cyclic models where universes expand, contract, bounce, and expand again. Time might be vastly older than our local patch of reality. Or it might genuinely have a starting point, a first moment beyond which nothing exists, not even emptiness. Because emptiness is still something, a space where things could be. True nothingness is incomprehensible. We're standing on a planet orbiting a middle-aged star in an average galaxy. The universe is expanding around us. Distant galaxies are receding faster and faster. Eventually, billions of years from now, they'll cross a horizon beyond which their light can never reach us. Future civilizations, if they exist, might look up and see almost nothing. No distant galaxies, no cosmic microwave background to study. They could conclude they're alone in a static universe. They'd be wrong, but their observations would support that conclusion. We're lucky. We live in an era where the universe's history is still visible. Time has given us a narrow window to understand it. That expansion is accelerating. Dark energy, whatever it is, pushes space-time apart faster over time. If that continues, the universe will keep spreading, cooling, dimming. Stars will exhaust their fuel. Black holes will evaporate over timescales that make billions of years look like eye blinks. Eventually, maybe, everything reaches a state of maximum entropy, heat death. Not a dramatic end, just a slow fade into uniform, meaningless stillness. Time would still exist technically, but nothing would happen. No change, no events, no way to mark one moment from another. Or maybe not. Maybe dark energy intensifies. The Big Rip scenario has expansion accelerating so violently that eventually it tears apart galaxies, then solar systems, then planets, then atoms themselves. Space-time itself shreds. What happens to time when the fabric it's woven into gets ripped apart? Does it end? Does it fragment into disconnected shards? We're speculating now, but the speculation is based on real observations of how the universe actually behaves. Here's what we do know for certain. Time, whatever it fundamentally is, behaves consistently within the framework we can test. Clocks tick at predictable rates, given their velocity and gravitational environment. Cause precedes effect in every observation we've ever made. The universe has a history that stretches back to a definable beginning point. Physical laws govern how systems evolve from one moment to the next. But knowing how time behaves isn't the same as knowing what it is. You can describe every property of water, measure its temperature, track its phase changes, write equations for its flow. That doesn't tell you why water feels wet. Time is weirder because we're inside it. We can't step outside and examine it objectively. Every thought you have about time happens within time. Every measurement takes time to perform. We're trying to understand the container from inside the container. Some physicists argue time is an illusion. Not that change doesn't happen, but that the flow, the sensation of moving from past through present toward future, is a trick of consciousness. The universe might be a static four-dimensional block where all moments exist simultaneously. Past, present, future, all equally real, equally existent. We only perceive a flow because our consciousness moves through the block, or because memory creates the illusion of sequence. If this is true, everything that will ever happen to you already exists, frozen in place within space-time structure. Your future is already written. You just haven't read that page yet. Others say no, time is genuinely dynamic. The present moment is uniquely real. The past existed, but doesn't anymore. The future doesn't exist yet. This view feels intuitive. Right now is happening. Yesterday isn't. Tomorrow won't until it becomes today. But physics doesn't clearly support this intuition. Relativity especially undermines it. If simultaneity is relative, if whether two events happen at the same time depends on your motion, then what does now even mean? Your now and my now might not align. Which present moment is the real one? These aren't just abstract puzzles. They touch something fundamental about existence. If time is an illusion, free will becomes questionable. If your future already exists, how can you choose it? If time is real and the future genuinely open, why does physics seem deterministic at so many levels? Quantum mechanics adds another layer. Particles exist in superposition until observed, occupying multiple states simultaneously. Does observation create the present moment? Does consciousness collapse probability waves into definite reality? We've built a technological civilization without answering these questions. GPS satellites account for relativistic time dilation, adjusting their clocks to match Earth's surface. Particle accelerators smash matter together at speeds where time visibly slows. We use time's malleability without understanding its nature. It works. That's often enough. But some mysteries demand more than practical answers. Time connects to every other deep question we have. Why does the universe exist? Why these laws of physics and not others? Is reality deterministic or probabilistic? What is consciousness? Every answer involves time. Every question assumes it. We can't think about existence without thinking in time. About time through time. The ancient Greeks had two words for time: chronos, quantitative, measured, sequential, the time of clocks and calendars, and kairos, qualitative, the right moment, time as experience and opportunity. We've spent centuries mastering chronos. We've barely begun exploring kairos. Modern physics reveals they might be the same thing viewed from different angles. Subjective experience and objective measurement, two sides of one phenomenon we're only starting to glimpse. Time's history is also our history. We evolved in time, developed consciousness that perceives time, built civilizations that track and value time. We're time's way of understanding itself. That's either profound or absurd, possibly both. What seems certain is that time's story isn't finished. We haven't reached any final answers. Every discovery opens new questions. Every solution reveals deeper mysteries. The universe is older than we thought a century ago. It's stranger than we imagined. Time bends, stretches, possibly ends, possibly cycles, possibly branches into parallel streams. We measure its passage with extraordinary precision while grasping its essence not at all. That gap between measurement and meaning defines our current understanding. We're incredibly sophisticated and fundamentally confused. And that's just the beginning. Because if time had a start, we need to understand what that moment was like. How do you create time itself? What would the first instant of existence even mean? The Big Bang marks the beginning of our observable universe. But was it truly the beginning of everything? The Big Bang isn't what most people imagine, not an explosion in space. Space didn't exist yet, neither did time. The Big Bang was the explosion of space itself, expanding from a state so dense and hot that matter as we know it couldn't form. And time began with it, or so the standard story goes. We've traced cosmic history backward, following the universe's expansion in reverse like rewinding a film. Galaxies converge, stars compress, matter heats. Around 13.8 billion years ago, everything we can observe occupied a volume smaller than an atom. Temperature and density approached infinity. Physics, as we understand it, breaks down completely. That moment represents a boundary, not just of matter and energy, but of time itself. Before it, the question might be meaningless. Before implies time already flowing. But if time began at the Big Bang, there was no before, no earlier moment, no preceding instant. The human mind rebels against this. We're wired to ask what came first. Causation runs deep in how we think. Every effect has a cause. Every beginning has something that triggered it. A universe springing from nothing, with time itself as part of what springs forth, feels incomplete. Cosmologists initially thought the universe might be eternal. Steady-state theory proposed continuous creation, matter appearing from nothing to fill gaps as space expanded. No beginning necessary, no awkward questions about first causes. But observations killed that elegant idea. The cosmic microwave background radiation, that faint afterglow of the Big Bang, proved the universe had a hot, dense origin. Steady state couldn't explain it. So we're left with a beginning, and beginnings demand explanation. Stephen Hawking approached this differently. Working with James Hartley, he developed what's called the no-boundary proposal. Imagine asking what's north of the North Pole. The question fails because you've reached a boundary where north stops meaning anything. Similarly, asking what came before the Big Bang might fail because time itself has a boundary there. In their model, time becomes space-like near the Big Bang. The distinction between temporal and spatial dimensions blurs. The universe has finite age, but no edge. No moment where time suddenly switched on. It's smooth all the way down. The Big Bang becomes less a beginning and more a limit, like the North Pole limiting how far north you can go. This sidesteps the causation problem by eliminating the need for a before, but it doesn't feel like an answer. It feels like a redefinition. We wanted to know what started time. We're told time doesn't have a start in the traditional sense. Technically satisfying, emotionally unsatisfying. Other theories take different approaches. Loop quantum gravity suggests space isn't continuous, but quantized, made of discrete units at the smallest scales. Apply this to cosmology, and the Big Bang singularity disappears. Instead of density and temperature reaching infinity, they hit a maximum limit. The universe contracts to an extremely small size, then bounces back, expanding again. Our Big Bang was actually a big bounce, the rebound from a previous contracting phase. What existed before? Another universe, same universe in its previous cycle. This trades one mystery for another. Instead of asking where time came from, we ask whether these cycles are eternal. Has the universe always bounced? If so, time has no beginning at all. It just is, stretching infinitely backward and forward. But eternal cycles create their own problems. Entropy increases with each bounce. Information accumulates. The universe should grow more disordered over time, yet we observe relatively low entropy in our current state, suggesting we're not infinitely many cycles in. So maybe the bounces do have a beginning, which returns us to the original question. String theory offers yet another picture. In some versions, our universe exists on a membrane, a brain, floating in higher dimensional space. Other brains exist nearby. Occasionally, they collide. When they do, the collision's energy creates what looks to us like a big bang. Matter and radiation flood into our brain. Time, as we experience it, begins. But time in the higher dimensional space, the bulk containing all these brains, was already flowing. Our universe's beginning isn't the beginning of time itself, just the beginning of our local time. Like a clock starting when you plug it in, time existed. Your measurement of it started. This pushes the question back without answering it. Where did the bulk's time come from? Are we just adding layers? Quantum mechanics introduces another possibility. In quantum field theory, empty space isn't truly empty. It seethes with quantum fluctuations. Virtual particles pop into existence and immediately annihilate, borrowing energy from the vacuum briefly, paying it back before the universe notices. What if our universe is a quantum fluctuation that didn't pay back the loan? In this model, the universe spontaneously tunneled into existence from nothing. Quantum mechanics allows this. Particles can tunnel through barriers they classically couldn't pass. Given the right conditions, an entire universe might tunnel into being. No cause, no trigger, just quantum probability making the improbable inevitable given enough time. Except there was no time for it to happen in. That's the paradox. Quantum fluctuations need time to occur. But if the fluctuation creates time, what does occur even mean? Physicist Alexander Vilenkin proposed the universe tunneled from literally nothing. Not empty space, not quantum vacuum, nothing. No space, no time, no laws of physics. And from that nothing, a small bubble of spacetime appeared, immediately beginning to inflate. This sounds mystical. It's actually following quantum mechanics to its logical extreme. If particles can appear from apparent nothing, why not spacetime itself? The math works. Whether the math describes reality is another question entirely. Each of these models faces the same core issue. They either push the beginning back, requiring something that already existed, or they invoke processes that seem to need time to happen, trying to explain time's origin using time. It's circular, frustrating, maybe inevitable. Some physicists argue time is emergent, not fundamental. At the deepest level, the universe might be timeless. Time emerges from something more basic, the way temperature emerges from molecular motion. Individual molecules don't have temperature. Collectively, they do. Carlo Rovelli and others suggest time emerges from quantum entanglement and correlation. The universe's fundamental description involves relationships between quantum states, not flowing time. What we call time is a bookkeeping device, a way of tracking how these quantum correlations change. At the foundational level, there's no time. There's just math. If time is emergent, asking when it began is like asking when temperature began. Temperature doesn't exist at the level of individual particles. It's a statistical property of many particles. Similarly, time might not exist at the universe's fundamental level. It's a property that appears when you have many quantum degrees of freedom interacting. This is intellectually satisfying to some physicists. It dissolves the question rather than answering it, but it creates new puzzles. How exactly does time emerge? What are the rules? Why does emerged time have the properties we observe, like flowing in one direction? We experience time as relentlessly forward. Causes precede effects. We remember the past, not the future. This time, asymmetry seems fundamental to existence, yet physics at its deepest levels is time-symmetric. Equations work equally well forward or backward. The arrow of time doesn't appear in fundamental laws. Entropy provides one answer. The second law of thermodynamics states that entropy, disorder, always increases in closed systems. This gives time a direction. The future is higher entropy. The past is lower entropy. We can tell which direction time flows by watching entropy rise. But this just moves the question. Why was entropy low at the Big Bang? A hot, dense, uniform state sounds high entropy. Actually, it's incredibly low entropy because gravity wasn't in equilibrium. Matter was smoothly distributed. Given gravity's attractive nature, that's extremely ordered. Over time, gravity pulls matter into clumps. Stars form, galaxies form, black holes form. Entropy increases. The Big Bang's low entropy state is what allows time's arrow to exist. But why did the universe begin that way? No current theory fully explains it. It might be random chance. It might be a requirement of whatever process created the universe. It might be an illusion, with our particular region of a larger multiverse happening to start low entropy, while others didn't. The multiverse enters many conversations about cosmic origins. If our universe is one bubble in an eternally inflating space-time, constantly spawning new universes, then our Big Bang was just one event among countless others. Time in the broader structure is eternal. Our local time began, but time itself, no beginning needed. This feels like giving up. If we can't explain our universe's origin, we invoke infinite others and claim the question doesn't matter. Maybe that's correct. Maybe we're parochial, assuming our experience reflects fundamental reality when we're actually one instance in an infinite ensemble. Or maybe the multiverse is unfalsifiable speculation, and we should stick to what we can potentially observe and test. The honest answer is, we don't know. We have sophisticated theories, beautiful mathematics, compelling arguments, but we don't know if time had a beginning. We don't know what beginning means in this context. We don't know if the question is even well formed. What we do know is that time, as we experience it, started with the Big Bang. Tracing backward takes us to a boundary where knowledge ends. Beyond that boundary, physics offers possibilities, not certainties. And maybe that's where we should leave it for now. Not because the question isn't important, because we're still gathering the tools to answer it. A few decades ago, we didn't know the universe was accelerating. We didn't have gravitational wave detectors. We couldn't image black holes. Each new tool reveals something unexpected. The nature of time's origin might require tools we haven't invented, observations we haven't made, theories we haven't conceived. Science progresses by admitting ignorance, then chipping away at it. But while the beginning of time remains mysterious, we understand something about its middle, the era we inhabit. Time flows here according to rules we've mapped with precision. Those rules are strange enough. Relativity shattered the idea that time is universal. Einstein showed that time is personal. It depends on motion. It depends on gravity. Two observers can disagree about duration, about simultaneity, about the order of events, and both be correct. This wasn't philosophy, it was measurement. Atomic clocks on airplanes tick differently than those on the ground. GPS satellites must account for relativistic effects, or they'd fail within minutes. Astronauts on the International Station age slightly slower than people on Earth. The differences are tiny, but they're real. Time dilates near massive objects. A clock near a black hole runs slower than one far away. At the event horizon, time slows to a stop from the perspective of a distant observer. Someone falling in experiences time normally, but watching from outside, they appear frozen, asymptotically approaching the boundary forever without crossing it. Which perspective is right? Both. Time doesn't have a single correct rate. It's relative. What you measure depends on where you are and how fast you're moving. This leads to strange implications. Imagine two twins. One stays on Earth. The other travels near light speed to a distant star and returns. When they reunite, the traveling twin is younger. They've both experienced time normally, but less time passed for the traveler. This isn't a trick or illusion. It's been confirmed experimentally with particles, with clocks, with everything we can measure. But wait. From the traveling twin's perspective, Earth was moving away and returning. Shouldn't Earth's twin be younger? This is the twin paradox. The resolution is that the situations aren't symmetric. The traveling twin accelerated, changed direction, experienced forces. That breaks the symmetry. Acceleration is absolute in relativity. Velocity is relative. The twin who accelerated is the one who ages less. Relativity doesn't just warp time, it merges time with space. They're not separate entities, they're dimensions of a single structure, spacetime. Events don't happen in space at a time, they happen at spacetime coordinates. Your path through life is a world line, a trajectory through 4 dimensions. This raises a disturbing possibility. If past, present, and future all exist as locations in spacetime, is the flow of time an illusion? Maybe all moments exist equally. We just experience them sequentially because of how consciousness works. The past hasn't disappeared. The future hasn't arrived. They're just elsewhere in spacetime, as real as distant places in space. This is the block universe view. Time is a dimension we move through, but all of it exists. The entire history of the universe, from Big Bang to heat death, is a static 4-dimensional structure. Change is illusion. Becoming is illusion. There's only being, stretched across time. Many physicists find this compelling. The equations support it. Relativity doesn't distinguish past from future at a fundamental level. Light cones define what can influence what, but they don't privilege now over then. Others reject it. Consciousness feels like flow. Causation seems to require change. Without genuine time passage, how do we explain memory, decision, intention? These might be illusions too. Or they might point to something relativity doesn't capture. Quantum mechanics complicates everything further. In quantum theory, systems exist in superposition until measured. A particle can be in multiple states simultaneously. When observed, it collapses to one outcome. But what does it mean for something to be in multiple states at once? And when exactly does collapse happen? Some interpretations say collapse is real and instantaneous. The act of measurement changes reality, but measurement takes time. How long? At what moment does superposition end and definiteness begin? The theory doesn't say. Other interpretations avoid collapse entirely. The many worlds interpretation suggests that all outcomes occur. The universe branches. Every quantum possibility spawns a new timeline. You observe one branch. Other versions of you observe others. All branches are equally real. If true, time isn't a single thread. It's a tree, constantly splitting. The past is definite because branches have merged into the trunk. The future is indefinite because branches haven't split yet. But this just relocates the mystery. What determines which branch you experience? Then there's the problem of quantum gravity. General relativity describes gravity as space-time curvature. Quantum mechanics describes particles and fields. Both theories work brilliantly in their domains, but they're incompatible. Attempts to combine them produce infinities and paradoxes. At the Planck scale, around 10 to the negative 35 meters and 10 to the negative 43 seconds, both quantum effects and gravitational effects become significant. Spacetime itself might become quantized, granular. Time might not be continuous but composed of discrete minimal units, Planck time intervals, beyond which shorter has no meaning. If time is quantized, what does that mean for flow? Does reality advance in frames like a film reel? Is there a shortest possible moment? Or does time remain smooth, with quantization affecting only what happens within it? Loop quantum gravity suggests spacetime has a foamy, discrete structure at tiny scales. String theory proposes extra dimensions and fundamental strings vibrating in them. Both attempt to unify physics. Both imply time might be stranger than we think. Neither has experimental confirmation. Perhaps time emerges. Maybe it's not fundamental, but arises from something deeper. Some theories suggest time emerges from quantum entanglement. When particles become entangled, their states correlate. As systems grow more entangled, temporal order emerges. Time is a feature of complexity, not a basic ingredient. If time emerges, it might not exist in the universe's fundamental description. The deepest laws might be timeless. Time appears only in approximate, large-scale descriptions. This would explain why it's so hard to incorporate time into quantum gravity. We're trying to describe something emergent using fundamental language, but emergence doesn't make time less real. Temperature emerges from molecular motion. Yet temperature is real, meaningful, measurable. Emergent properties can have causal power. Maybe time is the same, not fundamental, but no less real for that. There's also the question of whether time could flow backward. Thermodynamics says entropy increases. That gives time a direction. But microscopic physics is time reversible. If you filmed molecules bouncing and played it backward, you couldn't tell the difference. The laws work both ways. Entropy only increases statistically in large systems. A small system can spontaneously decrease entropy. It's unlikely but possible. So could a large system? Could entropy in a region decrease, reversing time's arrow locally? Probably not in any practical sense. The probabilities are astronomically small. But in principle, physics allows it. If you gathered all the air molecules in a room into one corner, entropy would decrease. Time's arrow would locally reverse. You'd never see it happen by chance. But the universe's laws don't forbid it. Black holes challenge time in other ways. Inside a black hole, space and time swap roles. The singularity isn't a place in space, it's a moment in time. Once past the event horizon, reaching the singularity is as inevitable as reaching the next second. You're not moving toward a location, you're moving toward a when. And at the singularity, time ends. Not in the sense that you run out of future, in the sense that time itself becomes undefined, curvature becomes infinite, physics breaks down. What happens there? We don't know. General relativity predicts singularities but can't describe them. Quantum gravity might resolve this, or it might reveal something stranger. Hawking radiation adds another twist. Black holes aren't entirely black. They emit radiation due to quantum effects near the horizon. Over enormous timescales, they evaporate. When a black hole evaporates, what happens to the information that fell in? Does it disappear? Quantum mechanics says information can't be destroyed. General relativity says it's lost in the singularity. This is the information paradox. Its resolution might require rethinking time. Some proposals suggest information is encoded on the event horizon in a holographic manner. Others suggest it escapes in subtle correlations in the radiation. Still others propose the information is truly lost, requiring modifications to quantum mechanics. Each possibility has radical implications. If the horizon encodes the interior holographically, spacetime might be an illusion. Reality could be fundamentally lower dimensional, with our three-dimensional experience emerging from processes on a two-dimensional boundary. Time would emerge too, from timeless holographic dynamics. The universe's end also involves time. If expansion continues accelerating, galaxies will drift apart. Stars will exhaust their fuel. Black holes will evaporate. Eventually, only cold, diffuse particles will remain, separated by unfathomable distances. This is heat death, maximum entropy. In such a state, does time still exist? There's no change, no events, no structure. Time requires change to be meaningful. In a maximally entropic universe, nothing happens. Time becomes meaningless, not because it ends, but because it stops mattering. Alternatively, quantum fluctuations might eventually produce a new low-entropy region. Given infinite time, even improbable events occur. A new Big Bang could spontaneously happen. Entropy would locally decrease. A new universe would begin. Time would reset, in a sense. But that requires time to continue through heat death. If time needs change and change ceases, does time also cease? Or does it persist as an empty framework, waiting for fluctuation to give it content again? Perhaps the question is malformed. Time might not be the kind of thing that can end, or begin, or persist. It might be a feature of how we describe reality, not a feature of reality itself. Asking if time exists without change is like asking if length exists without objects. The concept requires application. We navigate these ideas with mathematics and metaphor, but experience remains stubbornly present-focused. You exist now. The past is memory. The future is anticipation. That feeling of now seems undeniable. Yet physics finds no special moment called now. Every moment is now when you're in it. This is the mystery at time's core. It's the most familiar aspect of existence and the most perplexing. We move through it. We measure it. We feel it passing. Yet we can't say what it is. We can't explain why it flows forward. We can't prove it's fundamental. Every answer opens deeper questions, and the deeper we look, the stranger time becomes. We've seen time bend near massive objects. We've watched it emerge from quantum foam. We've traced its possible endings. But one question refuses to settle. Is time travel possible? Not the kind from movies, the real kind, the kind physics might allow. Start with the simplest case. You're already traveling through time, forward, 1 second per second. That's the baseline. But relativity showed something remarkable. That rate isn't fixed. Move faster, and your clock slows relative to someone stationary. Orbit a black hole, and you age slower than someone far away. When you return, you've jumped into their future. You traveled forward through time by taking a slower path through it. This isn't theoretical. Astronauts on the space station age slightly slower than people on Earth. GPS satellites must account for time dilation, or their positioning would drift. These are tiny effects, fractions of seconds, but they're real. Forward time travel exists. We've done it. The question is scale. Build a ship that reaches near light speed. Accelerate for years at 1 gravity. You'd feel normal weight. Eventually you'd approach light speed. Time aboard would slow dramatically relative to Earth. Travel for what feels like 10 years. Return home. Centuries might have passed. You've leaped forward. Physics allows this. Engineering doesn't. Yet. Backward time travel is stranger. General relativity permits closed time-like curves. These are paths through space-time that loop back on themselves. Follow one, and you'd return to your own past. Certain solutions to Einstein's equations contain them. Rotating black holes, infinite cylinders of dense matter, wormholes. Each presents a mathematical path to yesterday. But mathematics and reality diverge here. Every closed time-like curve requires exotic conditions, negative energy, infinite structures, configurations that might be impossible. Even if you built one, paradoxes emerge. The grandfather paradox is the classic. Travel back, prevent your own birth. Then you never exist to travel back. Contradiction. Some propose the universe prevents this. Perhaps quantum effects destroy any closed time-like curve before it forms. Perhaps consistency is enforced. Hawking suggested a chronology protection conjecture. The laws of physics conspire to prevent time travel into the past, not because we've proven they do, because allowing it creates contradictions. Others embrace paradox differently. The many worlds interpretation offers an escape. Travel back. Your actions create a branching timeline. You kill your grandfather in a new branch. In that branch, a different version of you is never born, but you originated from another branch. No contradiction, just proliferating timelines. This pushes the question elsewhere. Are those timelines real? Do they exist physically or just mathematically? If they're real, time travel becomes navigating a multiverse. If they're not, the paradox returns. Wormholes offer another route. These are tunnels through space-time, connecting distant points. Relativity permits them. Quantum mechanics complicates them. A wormhole's throat tends to collapse unless threaded with negative energy. Negative energy exists in quantum fields, but only in tiny amounts under specific conditions. Whether you could gather enough to stabilize a traversable wormhole remains unknown. Even if you did, there's a catch. Creating a time machine requires moving one wormhole mouth at high speed or near a gravitational field. Time dilation affects that mouth. Eventually, the two mouths link different times. Enter one, exit the other in the past. But you can't go back further than when the time machine was created. No visiting dinosaurs, no witnessing the Big Bang, only loops within the machine's operational lifespan. This limits paradoxes. You can't travel back to kill your grandfather before you were born. The machine didn't exist then. You're confined to a window. Consistency might be preserved by construction. But there's a deeper issue. If time machines are possible, where are the time travelers? Why hasn't anyone from the future visited us? Maybe they have. Maybe they're subtle. Maybe we wouldn't recognize them. Or maybe time machines are simply impossible, and every loophole closes under scrutiny. Quantum mechanics adds yet another layer. Particles don't have definite pasts. Their histories are superpositions. An electron's path through a double slit includes both slits simultaneously until measured. Its past is ambiguous. Does this mean particles experience time differently? Some interpretations say particles don't experience anything. They exist in abstract state spaces. Time is a parameter in equations, not a dimension they traverse. Measurement collapses possibilities into one. The past becomes definite retroactively. This suggests something unsettling. The past might not be fixed, not in the way we assume. At quantum scales, it's fluid until observed. Does this extend to larger scales? Probably not. Decoherence makes macroscopic pasts definite, but the boundary is fuzzy. Exactly when does the past crystallize? Then there's retrocausality. Some quantum interpretations allow future events to influence past ones, not in a paradoxical way, but in a self-consistent loop. An experiment's outcome might depend on a choice made after the particle was detected. The future reaches back. Causality becomes a loop, not an arrow. This isn't mainstream. Most physicists favor interpretations without retrocausality, but the math permits it, and experiments testing it yield strange results. Not conclusive, not violations of causality, but hints that time's structure at quantum scales is weirder than intuition suggests. Consider block universe again. All moments exist equally: past, present, future. If this is true, changing the past is incoherent. The past exists as surely as the present. You can't change it any more than you can change a distant location by walking somewhere else. You'd simply be part of the past you remember changing. Consistency is automatic, but subjective experience resists this. We feel the present moving. We remember the past, not the future. That asymmetry demands explanation. Even if block universe is correct, why do we experience time this way? One answer involves entropy. Memory formation increases entropy. Brains are entropy-generating systems. To form a memory, you must create structure, neuronal patterns. That requires dissipating energy. Entropy increases. This only works in one direction. Entropy's arrow aligns with memory's arrow. We remember the past because that's the direction entropy was lower. If entropy decreased, would we remember the future? In a contracting universe where entropy reverses, would inhabitants experience time backward? They'd think time flows forward from their perspective, but relative to us, they'd be aging in reverse. Their memories would point toward what we call the past. This is speculative. Entropy might not reverse in a contracting phase. Even if it did, conscious experience in such conditions is impossible to predict. We're built for increasing entropy. Reverse it, and the chemistry of thought might not function. Time's nature remains elusive. We've traveled from Einstein's relativity to quantum mechanics, from the Big Bang to heat-death, from closed time-like curves to block universes. Each framework offers insight. None provides a complete picture. Perhaps time is emergent. Not fundamental, but arising from something deeper. Space might be the same. Some theories propose spacetime itself is a hologram, projected from a lower dimensional boundary. Time and space would be illusions, useful approximations of a more abstract reality. If this is true, asking what time is becomes like asking what temperature is. Temperature emerges from molecular motion. It's real and useful, but it's not fundamental. Molecules don't have temperature. Collections do. Maybe time is similar. It emerges from quantum entanglement or information flow. Individual events don't have time. Systems do. This shifts the question. Instead of what is time, we ask what gives rise to the experience of time. What structure in reality makes temporal flow appear? We don't know. Candidates exist. Entanglement growing over interactions. Information propagating through networks. Entropy increasing in subsystems. Each offers a piece. None is complete. The mystery deepens when consciousness enters. You experience now. That experience feels undeniable, but physics finds no now. Every moment is equally real in relativity. Quantum mechanics describes states, not moments. Where does the feeling of presence come from? Some argue consciousness creates time, that the flow exists only in awareness. Without observers, the universe is a static block. Time is the motion of attention across it. This is radical. It makes mind fundamental. Most physicists reject it. But the hard problem of consciousness remains unsolved, and its entanglement with time is undeniable. Others suggest time creates consciousness. That awareness requires temporal flow. Memory requires past. Anticipation requires future. Selfhood requires continuity. Without time, no mind. This seems more plausible. But it doesn't explain why time flows. It assumes flow and builds consciousness on it. We circle back. Time is the stage for everything. Yet we can't define it. We measure it with clocks. But clocks measure change. Time is whatever allows change. But change is variation across time. Circular. Maybe that's the answer. Time is primitive, undefinable, like existence itself. You can't define existence using simpler terms. You can only point at it. Same with time. It's the framework within which pointing happens. Or maybe we're asking the wrong question. Maybe time isn't a thing to be defined. It's a relation, a structure, the way events connect. Not a substance, but a pattern. You can't touch a pattern. You can't isolate it. But it's real. The universe began. It evolves. It might end. Through all of this, time is the constant companion, the silent dimension, the unseen river. We're carried along it, measuring its flow, theorizing its nature, never quite grasping it fully. Every clock ticks forward. Every memory points backward. Every hope reaches ahead. Time is here, undeniable and inexplicable. We live within it. We are made of it. Our thoughts occur in it. Our understanding grows through it. And perhaps that's enough. To know time is to experience it. To measure it is to participate in it. The mystery doesn't diminish its reality. It deepens our wonder. The story of time is our story, from the first moment to the last, from singularity to entropy, from quantum foam to cosmic silence. Time weaves through it all, connecting every event, every particle, every thought. We may never fully answer what it is, but we'll continue asking, because asking is something only beings embedded in time can do. The question itself is temporal, an attempt to understand the very thing that makes understanding possible. Time remains, we remain within it, and the mystery, beautiful and profound, continues forward. Time remains, we remain within it, and the mystery, beautiful and profound, continues forward. We started with a simple observation. Time passes, clocks tick, moments accumulate into hours, days, lifetimes. This seemed solid, knowable, but every answer we found revealed deeper strangeness. Time bends near massive objects. It dilates at high speeds. It might have begun with the universe or existed eternally. It could be fundamental or emergent, real or illusory, a dimension we traverse or a feature of how we process reality. We've measured it with extraordinary precision, split seconds into billionths, then trillionths, built clocks accurate to 1 second in the age of the universe. Yet precision isn't understanding. We've mapped time's behavior without grasping its essence. Every civilization has grappled with this. Ancient astronomers tracked celestial cycles. Philosophers debated becoming and being. Modern physicists probe spacetime's structure. The tools change. The mystery persists. Perhaps that's appropriate. Time touches everything. It's prerequisite for causation, for memory, for change. To fully understand time might require standing outside it, but we can't. Every thought about time occurs in time. Every theory develops through time. We're trying to see the glasses we're wearing. Still, we've learned remarkable things. The universe has a history stretching back 13.8 billion years. Space and time are woven together, bending under mass and energy. Entropy gives time direction, marking past from future. Quantum mechanics hints that reality at its deepest level might be timeless, with time emerging from something more fundamental. These aren't small insights. They reshape how we understand existence. They reveal a cosmos stranger and more subtle than common sense suggests, but they don't resolve the central question. What is time? Maybe there's no answer. Not because we're not clever enough, because the question reaches bedrock. Some things can't be defined, only experienced. Existence is like this. You can't explain what it means for something to exist using concepts that don't already assume existence. Time might be similar, primitive, foundational, the ground on which all other concepts stand. Or maybe we're missing something, a perspective we haven't considered, a theory we haven't developed. Physics has surprised us before. Space isn't absolute. Matter is mostly empty. Light is both wave and particle. Each revelation seemed impossible before it became obvious. Time might hold similar surprises. Future discoveries could reframe everything, show us that what we call time is actually something else entirely, or confirm that it's exactly what it seems. Fundamental, irreducible, the arena where reality unfolds. For now, we live with uncertainty, and that's not defeat, it's honesty. The universe doesn't owe us answers, it simply is. Our job is to observe, to question, to test, to refine, to accept that some mysteries take centuries to crack, others might never yield, but the search matters. Each question we ask expands understanding. Each measurement constrains possibility. Each theory, even if wrong, teaches us something about reality's structure. Time will continue, with or without our comprehension. Clocks will tick. Entropy will increase. The universe will evolve toward whatever future awaits it. Heat death, big crunch, something we haven't imagined. And through it all, we'll keep asking. Because that's what conscious beings embedded in time do. We notice patterns, we wonder why. We build models and test them against reality. Sometimes we're wrong, sometimes we're right. Always, we're reaching toward understanding. The story of time is incomplete. It began before we arrived to witness it. It will continue after we're gone. We're observers in the middle, looking backward toward origins we can barely glimpse, and forward toward endings we can only calculate. That should be humbling. And it is. But it's also exhilarating. We're part of this, made of atoms forged in ancient stars, conscious arrangements of matter capable of contemplating time itself, the universe examining itself, time becoming aware of time. Whatever time ultimately is, dimension, illusion, emergent property, fundamental feature, It's the canvas on which everything meaningful occurs. Every decision, every discovery, every moment of beauty or horror or mundane existence. You're experiencing it right now. This moment, already becoming the past as you read these words. The future approaching, unknown and inevitable. Time flowing forward, carrying you with it. That flow might be illusion. All moments might exist equally in spacetime's block, but the experience of flow is real. Real enough that you've spent this time thinking about it. Real enough that we've built civilizations around it. Real enough that its nature remains the deepest question we can ask. So the mystery continues, as it should, as it must. Time doesn't surrender its secrets easily. But every secret we uncover brings us closer to understanding our place in the cosmos, our nature as temporal beings, our strange privilege of existing in a universe where time flows, change happens, and consciousness emerges to witness it all. The clock keeps ticking, questions keep accumulating, answers keep shifting, and somewhere in that endless process, we find meaning. Not in final answers, but in the search itself. The human story unfolding moment by moment. The universe evolving from past to future. Time, mysterious and undeniable, making all of it possible.